And so before we do the homework, I'm going to try and do two things today. Go through the formula sheet that the College Board provides. So that may be something that you want to print off before the actual day of the test. And then some common student errors. Again, anytime I talk about, this is a mistake that kids make, that's not judging, that's not meant to imply anything. It's just, as a reader, we tend to see common mistakes over and over and over again. And clearly that means that concept was more difficult for kids. And I always look at it as like, perhaps I didn't teach it very well to my students if that many kids are making the same mistake over and over again. Perhaps as a teacher, I need to up my game a little bit. So here's the homework from last night. Past studies indicate that about 60% of trees in a forested region are classified as softwood. That makes sense to me living in Maine. A botanist studying the region suspects that the proportion might be greater than 0.60. Maybe leaning towards a hypothesis test, but let's just keep reading. The botanist obtained a random sample of trees from the region and conducted a test. Null hypothesis P equals 0.6 versus alternate hypothesis P is greater than 0.6. Yep, it's a hypothesis test now. I feel pretty good about that. The p-value of the test was 0.015. That feels like a relatively small p-value. Which of the following is a correct interpretation of that p-value? So let me just switch to my document camera here. Okay, so here's the problem. And down the bottom here, I've just said the null p is equal to 0.6. The alternative p is greater than 0.6. My p-value or my probability is 0.015. And I just made a little note to myself, we typically reject the null hypothesis in favor of the alternative. I don't like the word except. I think we talked about that one day when we were grading student papers. And I typically want to compare my p-value to my alpha level of 0.05. And then I make a decision. So it feels like here we would reject the null hypothesis in favor of the alternative. So let's go back and look at our problems here. This was a really good problem, and I almost swung and missed on that. So if it is true that 60% of the trees in a forested region are classified as softwood, 0.015 is the probability of obtaining a population proportion greater than 0.6. That actually felt okay to me the first time I read it, and I went fast. So I put a little question mark here. It didn't feel 100% comfortable, but it sounded okay to me. How's that? If it is true that 60% of trees in a forested region are classified as softwood, 0.015 is the probability of obtaining a sample proportion as small or as smaller than the one obtained by the botanist. That one didn't feel too good to me, so I sort of crossed that out. But I kind of zoomed in on the sample proportion. So I was pretty comfortable that wasn't the right answer, and it got me thinking a little bit more about, is A the best answer? If it is true that 60% of the trees in a forested region are classified as softwood, 0.015 is the probability of obtaining a sample proportion as large or larger than the one obtained by the botanist. And then it clicked. That felt really good to me. I went back here and crossed out A. It was the population proportion. That's really not what the evidence has talked about. So C feels much better to me. Let's just keep reading for the heck of it. If it is not true that 60% of the trees in a forested region are classified, yeah, that didn't really make too much sense to me. And then E, if it is not true that 60%, that really didn't make sense to me. So I think the best answer here is C. And I like to say to my students, when we do a hypothesis test, the first thing we write down is the null hypothesis. And I like to say to my students, I assume that's a reasonable number. And we typically wouldn't run a test unless we think that's not a reasonable number. So when I buy 10 gallons of gas at the local gas station, I feel like I have 10 gallons of gas, and I don't run a test unless, the needle on my car didn't move. So we only run a test if we think something's up, if we think that that's not reasonable. So really nice problem. And I like to say to my students, read all 5 answers always, even if A sounds good, or you think A is the correct answer. I'm sure you've heard all year long that language is super, super important in statistics, and precision of language. And I really liked A at first, and it wasn't 100% comfortable with it. So I kept reading. When I saw that, then I was sold. C was really the best answer. So really nice problem from Luke. I appreciate that. Had fun doing it, and I had to think about that one a little bit myself. So here's page 1 of your formula sheet. Hopefully you've been using this all year with your teachers in school, and that you're comfortable with it. You can use this on the AP exam this year, modified AP exam. Open book, open notes. So you can pretty much use theoretically anything you want. I'm going to have my students print this page and this page before the test. And if they feel like they want to put more formulas on here, that's perfectly fine. They can do that. Honestly, when students put note sheets together, note cards, I don't think it helps them all that much on the test itself. But I really do think it helps them study for that test. So I'm going to recommend that perhaps you want to print these out beforehand, and perhaps you want to add in some formulas or little notes, whatever you want. That's perfectly fine. So whatever you're comfortable with. The reality is you may or may not use this during the test. I don't know. I'm just speculating here. But it's not going to hurt to have it. It's not going to hurt to have little notes to yourself or whatever. And so feel free to go ahead and do that. So I guess right up here we have X bar, which is the sample mean. Kids know how to figure that out. Sometimes this nomenclature makes it look even worse, but that's a simple formula, and you've done that before. So these first two formulas are what I would call one variable statistics. And this is the formula for your standard deviation, and you probably learned that in September or something way back when. It's honestly not a nice, clean formula. And this n-1 introduces degrees of freedom, which is a really hard concept, actually. In September, I'm trying to get my students to understand that, and that's not so easy. So hopefully by now you're feeling more comfortable with degrees of freedom, when you dealt with means and t-tests and whatnot. I don't think you'd ever use that formula on the AP exam. 100% speculation. I know nothing more than you do. But the intent of the AP Stats exam is not number crunching. So my gut says you would probably get that number from a calculator, but it's there if you need it. And so those are one variable statistics. I'm going to say that these are two variable statistics. So here's my least squares regression line, y hat equals a plus bx. Make sure that you do, kind of have your hat on that. That's a predicted model. That's super important. And always identify your variables, what's x and what's y hat mean. Y bar equals a plus bx. I don't know if I know the name for that formula, but I do know that x bar, y bar, the average x value and the average y value, does always sit on the least squares regression line. So I guess I've used that formula in the past to solve for one of those variables. Could it show up on this year's free response? The answer is yes. So it's good to have, good to know. Here's my R value, my correlation coefficient. And again, that's not a nice, clean formula at all. Unfortunately, our calculators will get that number for us if we need it. So again, I'm totally speculating, but I don't think you would ever use that formula or plug in 20 numbers and grind it out. It feels like a pretty big time constraint, and I don't think that's going to happen. But strictly speculating, again, I know nothing more than any of you don't know about this year's exam. So here's kind of a neat little formula for slope, right? This is the same slope as right up here. Slope equals my correlation coefficient, my standard deviation of my y variable divided by my standard deviation of my x. We've defined slope for years, rise over run, delta y over delta x, lots of different ways, right? That's kind of a neat little way to identify slope. And there's kind of a proof behind it, but boy, it's way beyond the scope of the course. But again, could you use that? And the answer is yes. Again, I've seen it used before in multiple choice questions, but again, I have no idea what's on this year's exam. So that's kind of the formulas for what we call descriptive statistics. Sometimes I call it EDA, exploratory data analysis, basically the same thing. A couple formulas for probability here. We could say P of A or B equals P of A plus P of B minus P of A and B. You might have seen it that way. It really means the same thing here. This is just sort of nomenclature, and this is more in words. So that's a good formula. And, maybe from a Venn diagram or something point of view, that might be something where you would use that. This is the conditional probability. And I think I did that one day when I was doing probability. So you might need that for conditional probability. And again, you typically don't have to write the formulas down if you put numbers in and show us all your mathematics, but they're there if you need them. And that's very helpful. So now we get down to a discrete random variable. So mu of x, the mean, the expected value of x, is the sum of the outcome times the probability. Well, I think I did that a couple of times when I was doing my random variables. And again, if you look right above it, it says mean. So that's pretty good. Good to know. Here's the standard deviation of a discrete random variable. Again, not a nice clean formula. And if you need it, it's there. And if you don't need it, that's okay too. And then I guess we have a binomial distribution and a geometric distribution. I know Luke did one day on those. And in many ways, they're sort of similar. There's 4 conditions for each one of those. And in a binomial, it's you hit exactly 4 out of 10 shots or something like that. And geometric would be what's the probability that the first time you hit a shot is on your 4th attempt. So that's the big difference between those two. Here's the formula for binomial. Here's the formula for geometric. Those are a little bit trickier for me to memorize. I don't really need to as a stats teacher, but again, it's there if you need it. Your calculators will do both of those. So I wouldn't stress over any of these formulas. If you've studied them this year, great. And if you haven't, don't worry about it. Here's the mean. Again, sort of look up to the top of the column there. Here's the mean for a binomial distribution. Mu of x equals NP. Here's the mean for geometric. Mu of x is 1 divided by p. Both of those are somewhat intuitive, actually. And many times my kids are able to answer questions before I've even taught them this because it sort of feels like it makes sense. And again, over here, those are the corresponding standard deviations of each of those distributions. Again, binomial and geometric. So really, the intent today is to recognize what's on the formula sheet and how to use it. And you can write all over it like I'm writing all over mine. That's perfectly fine. So then we get into some, I guess I would call these sort of general formulas. And we're going to use this for sampling distributions and inference. So we take a standardized test statistic. A z-score is one of the, standardized test statistics. It's some sample statistic minus some population parameter all over the standard error. So notice that all the formulas that Luke and I did, I think it was really 1 week where we did 1 sample and 2 samples, hypothesis test, confidence intervals. Not all those specific formulas are given to you. This is somewhat general. But all the problems I did, if we named the test at the top of our paper, then we didn't need to use the specific formula here. So this is just sort of, these are somewhat general. All confidence intervals are built the same way. We start with some sample statistic and we add and subtract. Those 2 numbers multiplied give us the margin of error. critical value, that's going to be a critical Z or critical T, depending upon whether we're dealing with proportions or whether we're dealing with means. Standard error of the statistic, maybe another way to say that would be the standard deviation based upon the sample size or something like that. So when I multiply those two numbers together, I get the margin of error. So all confidence intervals, both 1 and 2 samples, are sort of built the same way. And they're built off of this sort of general formula. We did chi-squared one of the first couple of days. We're way back in March when we first met all you guys, but it's not on this year's test. So for the sake of time, let's not worry about the chi-squared formula. Okay, so here's page 2. And page 2 is really going to be, again, somewhat generalized formulas that you might use for confidence intervals and hypothesis test means and proportions. So if we have one population proportion, p hat, again, the parameter is the population. Think sample statistic, population parameter. Mu of all the p hats is equal to p. And that's for one sample. For 2 samples, mu of p hat 1 minus p hat 2 is p1 minus p2. If we know sigma, which sometimes we do and many times we don't, we could use those two formulas for the standard deviations. But many times we don't know sigma. So this might be a better formula, again, standard error, standard deviation, for 1 samples with proportions. Here's 2 samples with proportions. Now this is a nuance, and I think I covered this hopefully when I was doing 2 samples with proportions. I would use those 2 formulas for confidence intervals, 1 sample, 2 sample. When I do a 2 sample hypothesis test with proportions, how we calculate the standard error is a little bit different. We come up with what we call p hat combined. I think I did that. I know I did that in one of the problems that I did. But notice there is a difference between those 2 formulas for 2 samples with proportions. This would be more with confidence intervals, and this would be for hypothesis tests. So again, maybe when you're doing your studying, just make little notes to yourself. This is the formula we want you to use with 2 samples proportions with hypothesis tests, where we come up with what we call p hat combined. That's what we would use with 2 samples with confidence intervals. Down here we have, again, sampling distributions for means. So population parameter, sample statistic. Mu of all the x bars is mu. Well, that's good to know. Luke did that, I think, when he did central limit theorem and sampling distributions. Again, if we know sigma of x bar is sigma over radical n. Many times we don't know sigma. So probably many of the problems this year you did with 1 sample, to get the standard error, it's your standard deviation divided by square root of n. That may look a little bit more common than this. If we know sigma, we would use this formula, but many times we don't. So I'm going to have to use SX here, or my standard deviation. For 2 samples of 2 populations, mu of x bar 1 minus mu of x bar 2. Well, that's just mu of 1 minus mu of 2. Again, if we know sigma, I could use that formula to come up with the standard deviation. Many times we don't. And so over here, I can use, I can calculate the standard deviation of my 2 samples by S1 squared over N1 plus S2 squared over N2. And I can use that for both confidence intervals and hypothesis tests. A little bit different than up here, like I just talked about with proportions. So again, not all the formulas that you potentially could need are on this sheet. But I guess the general formulas or helping you sort of start the problem are all on this. And so this is newer this year. We used to have an older formula sheet, and I think this one's so much better. And my students did find it easier to work with. So we've been working with this all year, and they've been feeling pretty comfortable as to which formulas are on here and which aren't. The remaining formulas down here are not going to be on this year's test. This is what I call inference for regression. We might have done that like the first couple days, way back. It seems like a long time ago. It probably wasn't more than a couple weeks ago. So for the sake of time, let's not worry about those, and you won't be tested on anything like that on your exam. So let's not even worry about those, I guess. So that was kind of a quick walkthrough of your formula sheet. Again, hopefully you've been using that this year, during your tests and quizzes and whatnot. And again, I think I would maybe print that off between now and the AP exam. And you can make notes on it. It's open book, open notes. So do whatever you want. And if you want to add in all those specific formulas for inference, you can do that this year. So I've had this slide pretty much every day, and it's giving you some updated information on when your test is and all of those things. So for the sake of time, let's skip that. So what I wanted to do for the rest of today is talk about some common errors that students make. Again, this is not judging. This is not meant to be derogatory. These are just things that we see as readers, as graders. And kids lose valuable points every year on the AP exams by making some of these common errors. So I broke it down into the 4 different themes or threads. So exploratory data analysis, experimental design, probability and simulation, and then inference. And so I'm just going to kind of walk through these. If need be, I'll go over to my document camera and actually write some of them out, but many of them are pretty self-explanatory. So when we ask students to compare 2 data sets or 2 distributions or 2 graphs, many times students just list the 2 summary statistics, or they make a list of all the different, mean, median, mode, range, but they don't actually compare them. Well, almost always when we give you 2 different sets of data, we want you to say something like, the median of A is greater than the median of B. And so students many times just list those out, but they don't actually compare them. So make sure that, if you're given things and you're asked to compare, well, actually compare them. A is greater than B, they're both approximately equal, all of those things. So I'm just going to switch to my document camera here. If I need to write something, I will. When writing out the least squares regression line, students forget to write y hat and identify the variables. So, you might see a student do y equals 2 plus 4x. I'm just making that equation up. And they think that they've answered the question correctly, but they haven't put a hat on the y, meaning a predicted y value, and they haven't identified either variable. So the student thinks they've done it correctly. They don't have the hat, they haven't identified the 2 variables, and so they're not going to get full credit for that. When asked to describe a distribution, students should always comment on at least shape, center, spread. I think I had an acronym GSOX at one point. One of the problems I did, shape, center, spread. All the textbooks now talk about that. You probably heard that a million times. I like to have my students, mention outliers if they think exist. So outliers, if they exist, should be mentioned. And I also like to talk about gaps or clusters. So there's a big gap right in the middle of my data set. Like, why did that happen? And that could be pretty important. So most rubrics call for at least shape, center, spread. And we do want you to mention outliers if they exist. Show all of your work when calculating a z-score. I guess I could extend that to pretty much any problem on the AP Stats exam, right? Please show us your math, even if you're using your calculator, even if it's something you can do in your head. Please, please, please show us all of your math and setup. And I like to say, use your calculator to just check your numbers. How's that? Sometimes students write actually too much on a free response question, especially in sort of this first theme or thread here, the exploratory data analysis. Most of these questions you can answer in 1, 2, 3 sentences. There's no need to write 4 paragraphs. It feels like sometimes students just, they write and they write and they write and they write. As a reader or grader, I have to read everything on your paper, even if I think you're way off base, even if I think you're not going to earn any points. I have to read everything. And the problem with writing too much is sometimes you might say something wrong. And I have to read that, and I have to take that into consideration following the scoring guidelines, what to give you for that part of the problem. So I like to tell my students, short and sweet, answer the question asked. So make sure that you're answering what we asked you. Answer it in context. Well, you've heard me say that a couple thousand times, right? Last couple of weeks. And then move on. So short and sweet. If you can say it in 2 sentences in context, great. Say it in 2 sentences and move on to the next problem. There's no extra credit if you list a whole bunch of work or a whole bunch of statistics, a whole bunch of things that we're not asking for. There's no extra credit in any part of these problems. So write full sentences, write in context, be specific, but don't feel like you have to write, a short story. That's not what we're shooting for. Not understanding how and why we transform data to make it look linear and then interpret the least squares regression line. I'm not sure if Luke did that. It's a minor part of the course, but there's one part of the course where we, might have, clearly nonlinear data or something like that, and we take the natural log of both sides or one side or something like that. So I think I would review that. It's still in the scope of the course, and I think I would just make sure that you're comfortable with perhaps transforming nonlinear data and somehow making it look linear. So then we get down to experimental design, designing an experiment. I really enjoy this part of the course here. It's fun, and this vocabulary is super important here, super important. So sometimes students don't fully understand the vocabulary, and they use these words incorrectly. If you don't know how to use confounding variables correctly, just say it in plain English. So don't feel like you have to use the exact statistical term. If you're more comfortable just saying it in plain old English, just say it in plain old English. Perfectly fine. Sometimes students don't tell us exactly how they randomized. They just said, we randomly put, the data into 2 groups. Almost always we want to know how you did that. Did you use a random digits table? Did you use the random digitizer on your calculator? Did you put the names in a hat and shake them up? So if you have a question and it's talk about randomizing, I think I would not just say, I randomly put the 100 volunteers into 2 groups. I would be specific as exactly how did you randomly put those into the 2 groups. Confusing causation with statistically significant results. I did a problem where we had a really low p-value and it asked about causation. Well, we can only talk about causation when running an experiment. So just because we have statistically significant results, a really low p-value, doesn't mean that we can say this caused that. So understand the difference between an experiment and hypothesis testing and what the difference is between causation and statistically significant. There's many different randomizing designs that we could use, completely randomized design versus randomized block design or something like that, stratified random sample. So again, just understand the different vocabulary words and how we can apply those to different problems. Sometimes students confuse control groups with controlling outside variables. So when I did experimental design, one of the 4 things that I like to think about is control. We don't always need a control group, but we always need to control outside variables entering into our experiment, which could ultimately skew the results or something like that. So I do a nice Coke Pepsi taste test with my students in the middle of the year to try and get them to see that not all experiments need control groups. All experiments need us to control for outside variables entering into the experiment. So a nuance in language, but super important. Many times students think that an experiment cannot be double blind because someone needs to know what's going on. Well, someone does actually need to know what's going on. That is important, but almost always in AP stats, we want our experiments to be double blind so that the patients or subjects don't know what they're getting and the The evaluator doesn't know, but there's clearly a third person who knows exactly what's going on. So again, I know nothing about this year's exam, but I think almost always we want to have a double-blind experiment in AP Stats, if at all humanly possible. When asked to randomize, if we don't say use a random digit table or something like that, you can use any randomization method you want. I actually think putting the names in a hat and shaking them up works just as well, and it's easy to explain. If you use a random digit table, you have to talk about repeats and how many numbers and how do you go from row to row. It's just more expensive, much more extensive, and it takes more time. Using your calculator, kind of the same thing. You need to talk about repeats and when do you stop and do you do 001 or just 1, and much more complicated. If they just say randomize any way you want, I recommend to my students, put the names in the hat, shake them up, pick them out, and we're good to go. Confusing confounding and lurking variables. Many of the textbooks still have lurking variables, and I know almost all the authors, they're all great. Lurking variables is technically not in the curriculum, so I don't actually teach it in my class anymore. I used to, and I think all I did was confuse the students. So I think I would know what a confounding variable is, and I think I did that one day with the dentist or something in apples. I did a problem with that. I just don't use the word lurking in my class, and my students don't like it anyways. But clearly, confounding is important, and please understand, what a confounding variable is and how we can use that in experimental design. So up to our third thread, probability. I think when we were grading, what was it, Monday, we saw a student who was able to get the numbers right from the two-way table, and the student came up with the correct answer, but there was no work. And so the student went from an E essentially correct down to a P partially correct. So for all of the themes or threads, or for all problems, please, please, please show us all of your work. Just writing out an answer, circling it, what we call a bald answer, almost always does not get full credit, sometimes partial. It depends upon the problem, but we need to show your work. Even if you're adding, I think it was, we needed to add 3 probabilities or something to get the right number, and the student didn't do that. The student just circled whatever the right number was. I can't do that math in my head, 0.45. 0.59 or something. We want to see where you got those numbers, even if you took them right from the table, even if you can do that math in your head. Please, please, please show us your work. Sometimes in a two-way table, we ask, is this independent of that? And students try and answer it just in words. So they say something like, yes, this gender is independent of whether you have a job because they're not impacted by each other, or they're not independent because of some reason. There's really no way to correctly answer that without doing some mathematics there. So just watch that, in a two-way table probability problem, when we're talking about independence, we need to see some mathematics. You can't answer that just in words. Using calculator speak for their work, not correct statistical formulas. So binom, PDF, something like that. I know what that means, right? Because I'm a math teacher. That's really not good communication, and that's really not good statistical practice. Now, if you follow it, something like I think I reversed the numbers here. If you put numbers here and then clearly explain what each one of those parameters mean, then perhaps that's accepted. I like to tell my students, tell me what's going on. That's a binomial probability distribution function, something like that. Tell me what these numbers mean. When you use calculator speak, you run the risk of not getting full credit, especially if you don't identify all the parameters. So again, I'll leave that up to you and your teachers, but I would much prefer my students tell me just in words, Mr. Murphy, it's a binomial setting, blah, 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 blah. It's so much better than calculator speak. And again, we hopefully Luke and I have said this pretty much every day since we first met, not putting their final answers in full sentences and context. Always, 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 make it contextual, make it specific to the problem that we're talking about. Don't have these generic answers. I use those a little bit when I do inference, but I also try and at the very end tie it all in contextually. So for statistical inference, and Luke and I have spent a lot of time on that, students do not list assumptions or check conditions nor understand why they need to do this. Students have actually gotten much, much better at this. I've been a reader for years and years and years, and if you go way, way back, students really struggled with this first one here. I think our textbooks are much better. I think as a teacher, I'm doing a better job. Students are getting much better with this. So that's great. Hats off to you guys. You're doing much better when we grade your exams. But please make sure that you know exactly which conditions we need to check, and equally as important, if not more important, why we need to do that. When we give you raw data, and we want you to talk about, the shape of your distribution is at least approximately normally distributed or something. We need you to do a dot plot or a histogram or something like that, a quick sketch of the data. You can't just say, oh, I assume it's approximately normally distributed. If we're given the raw data, the data points, we need to see some sort of a sketch here, leading us to believe that you've plugged the points in and it is approximately normally distributed. So this one here is not showing their final work set up and stating their final answers from the calculator. So I'm going to cross that out because I've since changed how I teach it a little bit in my classroom. When we were doing statistical inference, if the first thing you've done, and it was the first thing I always did, like one sample hypothesis test with proportions, if you name the test somewhere on your paper, then you don't need to show the formula and you don't need to plug in all the numbers. You can then just go to your calculator, and get, the z-score and your p-value and all of those numbers and list those. So if you name the test, then you don't need to write the formulas down, and that's one of the reasons that they're not on the formula sheet. So I've been teaching the course for a while, and I'm a little old school, and I used to make my students do something a little bit different. So let's not read all of number 3. Let's just keep going on that. So question for item number 4 here. When students list their null and alternative, sometimes we see something like this, X bar is 27 or something like that. Well, both your null and alternative should be population parameters. So that should be mu, or it should be P equals 0.6 with proportions. So P hat here would be wrong, and of course X bar here would be wrong. So just watch that. We do see that a lot as students confusing sample statistics with population parameters. When I'm stating my null and alternative, these need to be population parameters. Number 5, not linking the p-value and significance level when writing their final conclusion. Students will say, we reject the null because our p-value is equal to 0.03 or something like that. Well, we really want you to link that to some significance level. Again, typically alpha 0.05, but not always. I've seen problems where alpha is 0.01, and sometimes alpha is 0.10. We want you to compare your significance level with your p-value and then make a decision. So sometimes stating, the p-value is really small or the p-value is large, it's not enough. We typically want to see that linkage to some significance level. And those are sort of 3 typical ones right there. Reversing their conclusion. When p is low, therefore we fail to reject the null hypothesis. No, when we have a low p-value, a small p-value, we reject the null hypothesis in favor of the alternative. There are other ways to phrase that. That's sort of my general phraseology, I guess. When p is low, we have convincing evidence to reject the null hypothesis in favor of the alternative hypothesis, something like that. So sometimes we see students kind of reverse those. And then finally, number 7 here, I don't like the word except in inference at all. There are other teachers who disagree with that, and that's perfectly fine. But we don't accept the null. We either reject or fail to reject. I don't like to accept the alternative. I like to say we reject the null hypothesis in favor of the alternative. I think the word accept is kind of too definitive, too concrete, too I definitely proved something, and that's really not what's happening in a hypothesis test. We have some sample data and we weigh the evidence. We run a test, we turn it into a p-value, and we try and make a decision. But we never know whether we've made the right decision sometimes until after the fact, and that's type 1, type 2 errors. And I think Luke did that one day. So let's just go back to the PowerPoint. I think it's almost that time. So I pretty much just walked through those common errors for the 4 different themes or threads in the class. Hopefully by now you're feeling more comfortable with how to use that formula sheet. I didn't go through the tables today, but you can use your tables. There's 2 pages of a z table, one t and one chi-squared. Of course, chi-squared's not on this year's exam, so don't worry about that. You can have that. You can have open book, open notes. And I think between now and the AP Stats exam, I would print that out, have it handy. Feel free to write other formulas if you want on your exam. That's perfectly on that formula sheet. That's perfectly fine this year with the modified exam. Again, similar to all problems in AP Stats, we should be able to write a clear, concise solution in context. Short and sweet, I like to say to my kids. Don't volunteer anything, answer the question at hand, move on to the next part of the problem. Here's your homework. I think this is interpreting a p-value, and Luke